In physics, the kinetic energy of a body is the energy that has due to its motion. It is defined as the work needed to accelerate a body of a given mass from rest to the speed. Having gained its energy during acceleration, the body maintains its kinetic energy unless its speed changes. For the body to return to resting state requires a negative work of the same magnitude as its kinetic energy. The adjective kinetic energy in the names comes from the ancient Greek word kinesis, meaning movement. The terms kinetic energy and words and its meanings come from the 19th century scientists. Early knowledge of these ideas can be attributed to Gaspar Gustav Coriolis, who in 1829 published an article titled Du calcul de l'effet des machines, outlining the mathematics of kinetic energy. The kinetic energy term is due to William Thomson, better known as Lord Kelvin, in 1849. There are various forms of energy, as chemical energy, heat, electromagnetic radiation, nuclear energy, gravitational energy, electrical, elastic, etc., all of which can be grouped into two types, the potential energy and kinetic energy. The kinetic energy can be understood better with examples that demonstrate how it is transformed from other forms of energy and other types of energy. For example, a cyclist will use chemical energy that provides food to accelerate his bicycle at a chosen speed. Its speed can be maintained without much work, except for air resistance and friction. The energy converts into the energy of motion known as kinetic energy, but the process is not completely efficient and the cyclist also produces heat. The kinetic energy of the moving bike rider can be converted into other forms. For example, the biker can find a hill high enough to climb, so to load the bike to the top. The kinetic energy so far used will have become gravitational potential energy, can be released rushing downhill on the other side of the hill. Alternatively, the cyclist could connect a dynamo to a wheel and generate electrical energy on the descent. The bicycle is traveling more slowly in the bottom of the hill because much of that energy has been diverted to make electricity. Another possibility could be that the rider applies the brakes, and if the kinetic energy will be dissipated through friction into heat energy. Like any physical quantity which is a function of speed, the kinetic energy of an object depends not only on the inner nature of that object, also depends on the relationship between the object and the observer. In physics, an observer is formally defined by a class particular coordinate system called inertial reference system. Physical quantities like these are called invariants. The kinetic energy is collocated with the object and that attributed to the gravitational field. The kinetic energy calculation is done in different ways depending on the use of classical mechanics, relativistic mechanics, and quantum mechanics. The proper way to calculate the kinetic energy of a system depends on its size and speed of the particles that forms. Thus, if the object is moving at a speed much lower than the speed of light, the classical Newtonian mechanics calculation will suffice for. But if the speed is close to the speed of light, the theory of relativity begins to show significant difference in the outcome and should be used. If the object size is smaller, quantum mechanics is more appropriate.